Let me... Yes.
I think we are live on YouTube and we can get started. Crisia, do you want to take over?
So, hi everyone, apologies for this delay, I have technical problems. So welcome again to the Condensed Matter Seminars, the Quantum Matter Seminars organized by Professor Adrian and me. And today we are very pleased to resume our activities with Alberto Nocera from Quantum Matter Institute, Stuart Blossom, and he's going to talk to us today about one-dimensional Kitaev magnets. So people usually enjoy 2D Kitaev systems, but today we are going to see it in 1D. So Alberto, thank you very much for accepting your invitation again. I think this is the second time we are giving us a seminar, isn't it?
I think it's the first time online.
All right.
Last time I gave a seminar at New was 2 years ago, before the pandemic started. So
good time.
Pleasure to be back.
Good time. So the stage is yours.
Okay, thank you very much, Crisia and Adrian, for the invitation and for the opportunity to speak about my recent work on the one-dimensional Kitaev magnets. And as you said, most of the times in the literature, the interest is on 2D Kitaev materials. And of course, and I'm trying to convince you, I hope at the end of this talk, I'm gonna try to convince you if also one-dimensional Kitaev magnets could be interesting. And so let me start from the acknowledgements to acknowledge my collaborators that basically allowed this work to be possible. And the main players would be Ian Affleck and Wang Yang and Tarun Tumuru at our institute, and Stuart Blossom Quantum Matter Institute in the University of British Columbia. But we also enjoyed a very fruitful collaboration with Heian Ki at the University of Toronto and Eric Sorensen at McMaster. And this is like the list on the right. You see the list of the work that we have done on this topic. Of course, I'm not going to be able to talk about all of them, but I hope to give a summary about what we have done. Yang Wang is in a kind of a box because he has been the main driving force on the theoretical side with field theory and other kind of calculation I'm going to tell you in a few minutes. So let me go to the outline of this talk. So in the first part, I'm going to try to introduce and motivate why one-dimensional Kitaev magnets would be interesting. And then I will go through the model that we have studied, that is a generalized Kitaev model with including of diagonal exchange or gamma interaction or Eisenberg interactions, and I will discuss the phases of this model, and then at the end I will talk about current work, the open questions, and the future direction we plan to study. So let me start from an introduction, right? So why we are interested in general in one-dimensional systems for many reasons, right? So, but one of the things I wanted to clarify here is that how kind of lower dimensional, in particular one dimension, is even possible to think about. And the lesson we learn in undergrad is about quantum confinement. That tells us that in the moment the energy scales in the we are working on are basically negligible with respect to the in the orthogonal direction to the direction we are interested in, and they are basically smaller than the particle wavelength. We are allowed to neglect higher to neglect dimensions. And here I'm just showing the basic lesson we learned in undergrad about the subbands that basically would appear in a three-dimensional system. For instance, in the very moment we quantized we quantized in the perpendicular direction where we are working on. Basically, one of the another very important motivation to why we are interested in one-dimensional system is that we know very well the physics of normal materials and normal matter in dimensions higher than one. And here, as you can see in this box, we can see that the fact that particles or degrees of freedom can avoid each other more easily in a higher dimension is very important for criticality, right? So, and here I'm talking about still the classical criticality. So I'm showing you the phase diagram of a normal material that shows, however, for specific values of temperature and some other parameter can show critical points. And the main feature of classical criticality, so we are sitting at the second order continuous phase transition, is the fact that we have an order parameter according to standard thermodynamics, and we basically, the fluctuation of these order parameters in real space they behave like power laws, so we have scale invariance. So we know very well classical system, normal materials, if you want, at criticality, right? So what's interesting about in 1D is that criticality is ubiquitous, right? In this case, for normal materials, criticality appears at special point in the phase diagrams, just a couple of them in this case, where I show basically the water phase diagram. But in one-dimensional system, we have an extended critical region in the phase diagram. And this is due to the fact that the microscopic level that particles, degrees of freedom, cannot easily avoid each other in 1D, so they are forced to interact very strongly between each other, and this gives rise to, at the macroscopic level, to basically a disorder state, a quantum critical state, we call it, that is in extended region of the phase diagram. And this criticality, quantum criticality in this case, because the scale invariance is not just in space domain, but is also in time, is a scale invariance in space-time, can appear also at finite temperature or ordinary temperatures, as I show you in this dome. And so in this kind of third axis of this kind of qualitative phase diagram of a quantum antiferromagnet. And so this talk is going to be about magnetism in one-dimensional system, where criticality is, especially quantum criticality, is ubiquitous, and this appears also as power law of any magnetic correlation functions that one can compute, right? So basically, one-dimensional system sit always, almost always at criticality. So they have a scale invariance behavior. So one of the most important examples of manifestation of this quantum criticality in 1D is the so-called spin-charge separation phenomenon. This is very well known, and here you can see on the left, I show you the separation of the degrees of freedom of the electron in its spin and charge. But of course, this is just a drawing. So what happens in condensed matter system is that while in dimensions larger than one, we have a well-defined dispersion relation for the electron, for the quasi-particles, as we say in the condensed matter jargon, that are very well defined, as I show you for instance, in copper metal from Wikipedia. Spin charge separation means that the electron as a excitation of the system in this kind of quantum critical state decouples into a spin degrees of freedom and a charge degrees of freedom, right? So and this is have been seen in real materials. But this talk is about magnetism, so let's discuss the most probably well-known quantum magnet in one dimension, and this is the Eisenberg model in 1D, as I show you in this equation. And if I and this is important because it's going to give us the most simple example of a disorder, a critical state that's called spin liquid, right? So that is a disorder state that appears at 0 temperature. So going back to the Eisenberg model, we can solve this the Eisenberg model classically in a very easy way. So we have two possible classical ground states corresponding to up, down, or down, up configurations. But as you can see, as we all know, as soon as we put quantum mechanics into the game, and we express the Hamiltonian as in quantum operators, we see that the spin flip terms, they force the system to fluctuate and to go away from these classically ordered states. And so basically what we say is that the classical nil state where we expect to see in a one-dimensional antiferromagnet is disrupted by the quantum fluctuation given by the spin flips. So this seems unwavering for now, but things has been put on a solid ground already in the 30s by Bethe, who proposed this Bethe ansatz and basically showed that quantum antiferromagnet in 1D has no long-range order, no-nil order. So there is no ordering of the spins, and basically it sits at criticality. So the spin-spin correlation in every direction, they show a power law behavior that I show here. And as a plus, and this talk is not going about excitation on top of the critical state on the spin liquid state, but to show you a demonstration that this is seen in reality, this particular state, this quantum spin liquid, shows like fractionalized excitation in a very similar way as I was telling you before about spin-star separation. And this is called spin-on excitation. So the excitations are fractionalized, so they are not like, as I show here in this plot, they are not just classically antiferromagnetic waves with a very well-defined dispersion relation, but they are a continuum of excitation of these basically domain walls that can be created if I flip a spin on top of this non-trivial ground state that characterize this model. So, and here is just an example again about why 1D physics is interesting. And here in this other slide, I show that this behavior that I was telling about one-dimensional antiferromagnets is really seen in various experiments and several materials, and is very well known, right? So another important phenomenon and actually setting we are interested in for the sake of this talk is frustration in magnetism. And here I show you the classic representation of a frustrated antiferromagnet where the third spin doesn't know where to align if other two spins are aligned already antiferromagnetically aligned in a triangular lattice structure. And in 1D, we have an important, very important paradigmatic example of this behavior that is given by the J1, J2 Eisenberg model that I'm not going to tell you about. But I'm showing you this just to mention that besides unconventional disorder states like the spin liquid I was telling you a minute ago, we have also unconventional orders in one dimension. They are very non-trivial. One of the example of this is the spiral order that appears in this very simple model in one dimension. And again, there is no conventional magnetic order, dipolar order, but these spins can basically rotate as in a spiral. And in turn, and this state that is an order state competes with a very much more complicated state of matter where we have again a disorder a disorder ground state configuration, but we have also multipolar power law correlations, right? So, and here on the right, I'm just showing you the phase diagram of this very simple model that it starts to just give you an idea that even a very simple model in one dimension can give rise to a very complicated phase diagram. And so so I talked to you about two ingredients, frustration and spin liquids. And so let me go to what's another very important reason why we are interested in 1D physics. And this is the fact that we have many analytical and numerical exact approaches that we can use in 1D. And one that I already mentioned is the Bethe ansatz that was proposed in 1930s. Of course, we have more, done a lot of developments since then, but it's still one of the most important methods we have in one dimension. There are a class of field theory methods that I will touch upon that are kind of can be summarized by the word bosonization, and I will tell you about a little bit more later in the talk. And from the numerical point of view, we have perhaps the strongest numerical method that we could use to attack the many body problem in one dimension, that is the density matrix renormalization group. That we now know that is based on a matrix product state wave function ansatz for the many body wave function. And so so this is as I was telling you, I talked about spin liquids and frustration. Let me go closer to the main subject of this talk, that is about Kitaev spin liquid and Kitaev magnets in general. And so all this story started by the very famous Kitaev model on the honeycomb lattice that is on 2D, and that has this peculiar. So I'm sure you have seen these slides so many times in the recent times. So, but I'm going to show you this again. And as the Kitaev model is given by this model where we have bond-dependent exchange interaction that can be going into X, Y, or Z direction. So again, this realizes a different kind of frustration that is a bond exchange frustration, because the center spin here, if you think about it, doesn't know where to go if he wants to satisfy at the same time the constraints given by the exchange by these three bonds, by the three bond combination. And why this is important, I will summarize it very quickly. This can be solved exactly in terms of Majorana fermions. And among these Majorana fermions, that are 4 of them, one is free. So there is underneath this model, there is a gapless abelian spin liquid with a gapless like cone-like band structure. That is already very interesting, but Kitaev at the beginning was interested in what happens when we apply magnetic field, and he showed that you can tune the system to a gap non-abelian spin liquid. And why this is interesting is because Kitaev himself, he went ahead and he showed that this gap non-abelian spin liquid can sustain non-abelian excitation on top of a chiral Majorana edge state that sits at the boundary of this hexagonal lattice. But that's not the important part. The important part is this non-abelian fermionic excitations. And in terms of this non-abelian fermionic excitation, one can, in principle, realize what's called the topological quantum computer. In such a way, operation on these non-abelian anyons can be naturally protected from the decoherence coming from the environment. So that's why we are very interested in understanding Kitaev magnetism in general. However, reality is much different from the Kitaev model. And yeah, so but besides that, now we have a kind of recent years shown that now we have a roadmap where to look for Kitaev materials. And in here, I'm showing you a phase diagram in terms of correlation and spin orbit coupling, where we know now we now know that to look for Kitaev materials in real life, in real materials, we need to look for materials that have strong electron-electron interaction and spin-orbit coupling. And here I'm showing you the usual scenario that appears in certain transition metal oxides, like the iridium oxide, for instance, that have a 5d5 configuration. And because of octaedral crystal field, the spin-orbit coupling, that can be thought of a J effective equals to 1/2 spin-orbit induced Mott insulators. But besides the fact that correlation and spin-orbit coupling has to be strong, what was realized by Giachelli and Gaglionin almost 10 years ago is that the coordination also of the material under consideration is important to find Kitaev materials in real life. And in fact, we have in general two possibilities for this transition metal oxide materials, like the iridates, or for instance, the ruthenium chloride, that's the rutenates, if you want, the ruthenium chloride material. And one is the corner sharing possibility, and one is the edge sharing. We are interested mostly in the edge sharing case, where it has been shown by these fantastic works that at low energy, if you project the physics, the project here, the degrees of freedom, and you are just interested in the low energy physics of these materials, you get the Kitaev model plus corrections, right? That's what I will talk about this in much more detail in a second. But that's the main theme of my talk, and basically is also a subject of intense research recently to try to understand the role of this correction on top of the Kitaev term. And again, so the three main ingredients are strong electron-Coulomb interaction, spin-orbit coupling, and also bond directional exchange, right? So, and also coordination and sharing in this transition metal oxide that gives rise to bond directional exchange. These are the main ingredients to find Kitaev, the Kitaev model in real materials. However, reality, as I was mentioning a second ago, reality is much more complicated than that. And basically what these candidate materials, Kitaev candidate materials, they don't show long range, or they don't show the long sought spin liquid ground state that everyone is looking for, but they show a magnetic order, right? And here I'm showing this specific heat versus temperature map of the famous ruthenium chloride on the left-hand side, where of course there is a peak associated with the Neal ordering temperature. So this material has a zigzag magnetic order, not a Kitaev spin liquid. A spin liquid in its ground state at lowest temperature. But however, it was proposed recently that, and there have been many talks about this, that this magnetic order can be suppressed by inducing a magnetic field, and the hope is to kind of unveil the Kitaev phase, the Kitaev spin liquid phase underneath the fact that one applied the magnetic field. On the right-hand side, instead, I'm showing you that in the same material, recently also pressure has been proposed as a kind of factor to suppress basically the effect of this correction on top of the Kitaev term that kind of are spoiling the Kitaev spin liquid phase that we expect to find. So pressure is another kind of candidate, if you want, if allow me this this term to basically try to realize the Kitaev spin liquid state in real materials, right? And this paper down here that I mentioned here is also a theory paper that as mentioning pressure as another can have another key role into this game of suppressing the gamma and J, the corrections on top of the Kitaev model. And so So what do we know about the phase diagram in 2D, about the Kitaev model? We know kind of quite a bit. Here I mentioned one of the papers that I'm more familiar with, that is this paper by Jeffrey Rao and Heian He, that shows the results of the phase diagram in 2D. And now I'm going to talk about these phases, and this is a very complicated phase diagram that is a function of j, k, and gamma parameterized in this way. That's why this phase diagram was put on a sphere. And we're going to show a phase diagram like this for the one-dimensional case later in the talk. So what I just want to say in this slide is that the real material seems to appear with the ferromagnetic Kitaev interaction and an antiferromagnetic gamma interaction, right? And the Eisenberg J seems to play a minor role. That's what I wanted to say here. And also, real materials look to appear in this kind of region in the phase diagram. But one of the motivation of this talk was to study the Kitaev model in one dimension. And why is that? The reason is that there is recently a hot debate in the literature about the role of the gamma into the phase diagram. So many different papers have proposed different phases around this region of the phase diagram. That is basically the region where the gamma term is kind of dominating, and again, this is everything in 2D, and the hope is that by approaching this problem by a one-dimensional perspective, we could make some progress with respect to this many proposal and many different results that have appeared recently in these many other works. And so basically, let me start with all this motivation. Now let me start my my investigation of a one-dimensional version of the Kitaev Eisenberg gamma model. Basically, what we do is we cut the chain, a zigzag chain inside the hexagonal honeycomb lattice. And we study just that, right? So we neglect completely the possibility of the Z exchange, if you want, the coupling into the vertical direction in this drawing. And we basically consider this model along this chain. Very simple, right? So it's a very simple model. However, highly frustrated. And we're going to see that there are many phases, very complicated actually phases that are going to appear in the phase diagram. And so, so the first thing I want to say is that I'm going to put aside, if you want, the Eisenberg term J for a second. So I will study the Kitaev gamma chain initially, and I will put J at the end into the game. So for now, I'm going to neglect the effect of the Eisenberg exchange interaction. And so we start from this model now that we put on a chain. And so this is represented in this way, where this XY are the, if you want, the Kitaev exchange terms. And the gamma are not represented in this drawing, but as you can see, this is as a two-side unit cell, right? The first trick, very important trick that one should apply to try to solve this model is so-called is a unitary transformation that is called six sublattice rotation. It's a local transformation beside the appearance, and basically this implies that into the spin space, you do a rotation in spin space. This x, y, z refers to spin operators. You do a very peculiar rotation in spin space every 6 sides. So every 6 sides you rotate your spin operators and then you repeat, right? At the end of this game, that is very nice to do, you get a transformed Hamiltonian that has the same physics as the original one, since it's a unitary transformation, but that's a very different structure from the one that we started from. And actually has a 3-side periodicity, as you can see here. the Kitaev term is not modified much except for the sign. So k goes in minus k after this transformation. The gamma also changes sign if you want, but then a very important part is that the frustration, the off-diagonal exchange frustration of the gamma is basically kind of adjusted in the sense that here it appears as a much more symmetric perturbation to the Kitaev term. So it's alpha alpha beta beta, right? As you can see here in this after this transformation. So it looks like much more symmetric, and again, so these are the main this is the starting point of the investigation to do this transformation. So from now on, I'm going to work always into this rotated frame. But I will at some point touch base and say what's happening in the original frame. And you, of course, you can ask questions and then stop me at any time. And so another important property of this model is this so-called equivalence here that I'm showing here. So basically one can prove by doing another unitary transformation that I'm not going to tell you about, that the parameter space of the model K gamma maps exactly into itself. The physics of the problem, if you want, is invariant by changing the sign of gamma, right? This is true only in one dimension, and it's not true if we couple chains together or we go into the two-dimensional two-dimensional model. And so I'm going to parameterize K in gamma with cosine phi and sine phi, as in the usual, as usual. And so this equivalence here means that the phase diagram with phi between 0 and pi is equivalent with to the phase diagram with phi between pi and 2 pi. So very easy. But all this equivalence and this kind of 6 sublattice rotation transformation that we have done allows us to already see what are the hidden there are the hidden symmetric points into our phase diagram. And the first two are the so-called hidden ferromagnetic points. In fact, if phi is pi over 4 or 7 pi over 4, you can see that H prime is a ferromagnetic Eisenberg model. So K becomes equal to gamma, but they are both negative. And instead, for phi pi over 4 and 3 pi over 4, we unveil basically two antiferromagnetic hidden points, right? So we already discovered that there are 4 special points in the phase diagram that have simple properties, right? They are equivalent to a ferromagnetic or an antiferromagnetic Eisenberg model, and that's very important, right? For what I'm saying into the next slides. And so basically, given all this kind of introduction, I'm going to kind of anticipate the whole phase diagram of the Kitaev gamma chain. Again, for now, the Eisenberg J is still turned off. Basically, there are mainly 3 phases, if you want, right? So there is one phase that is kind of this pink phase. And here I'm going with the phi between 0 and pi, starting from 0 to pi here. So I'm not putting the phase diagram on a circle. That would be more natural, but I like it more this kind of different representation. So here on this line, we go from K to minus K, and we have positive gamma, right? Antiferromagnetic gamma. And so as I said before, we have an antiferromagnetic point and a ferromagnetic one. So there is a disorder, gapless phase that occupies basically 2/3 of the phase diagram. They're gonna discuss with you in a second. And then there are order phases, right? So close to the antiferromagnetic Kitaev point, we have order phases, and close to the ferromagnetic Kitaev point, we have disorder gapless phases in a very kind of similar fashion as in 2-dimensional case. You might notice that there are this kind of dashed blue lines close to the 2 Kitaev points. And here, those are so-called Kitaev phase that we verified that they extend for a finite for a finite region of parameters close to the Kitaev points. It was not our initial intention to study these regions, and that constitutes ongoing work at the moment. But what I can anticipate for you is that, of course, at k and minus k, we have an exact solution again, as into the dimensional case, but the characterization of the neighborhood, the phase in the neighborhood of this point is much more complicated because we don't have conventional order parameters or even string order parameters or more complicated way to characterize this phase. So I left it as a kind of dashed lines to tell you that is basically ongoing work. And so let me focus first on this disorder gapless phase, where I also put emergent, SU2 level 1 and CFT. I put some like I put some names to this phase, and I'm gonna try to justify these names. Yeah, before I go into that, there is a transition point that I call it here phi c around 0.33 times pi that I verified numerically to show a divergence in the second derivative of the ground state energy with respect to the angle phi. And so I can anticipate to you, actually, this demonstrates that there is a first order phase transition between this disordered gapless phase and the order phases that I'm going to discuss later. And so before I go into the discussion in the disordered phase, gapless phase, there is a review of field theory that I need to do, otherwise it's difficult to explain. And so the basis is the Wess-Zumino-Witten model that probably some of you are familiar with, but some others don't. And but this constitutes the standard for a low energy field theory for the antiferromagnetic Eisenberg model in one dimension. And basically, the idea is that you start with an Alberg model with spin up and spin down spins at half filling. So we have 1 electron per site, and you turn on of course, the electron-electron interaction. So you open a gap at the Fermi level. So the only degrees of freedom that you are left at low energy are not the charge degrees of freedom, if you want, but you are just left with the spin degrees of freedom ruled by the J that is proportional to T square over U, as shown also in Bethe-Ansel calculation. So the main idea is to make use of this simple picture here to write a field theory for the low energy of the Eisenberg model. I'll try to be more clear in the next slide. And so what happens is that it's possible to show that if you have a Dirac fermion, so a spinful fermion, you can decouple your, here I wrote an action and a Lagrangian. Unfortunately, it's like, I'll try to show also Hamiltonians later on, but this kind of approach is introduced in the field theory using Lagrangian and actions. But basically what happens is that, as I was telling you before, when you gap out the Alberg chain with a finite U, you basically can write down this in a field theory language as a charge boson that becomes gapped because of the cosine term. And actually Witten in 1984 showed that what you are left out at low energy is another degrees of freedom that is an SU2 matrix that has to do with the Eisenberg model, so to speak. Is a very kind of waving and qualitative introduction to this, but there are several pieces, but the most important part is that this can be solved, right? So this can be solved, right? It is a quadratic. Besides the appearance, it's a quadratic action, so it can be exactly solved, right? And so we made use of this and to basically solve our Eisenberg model. And again, I'm going back to Eisenberg because I'm trying to solve our problem around the antiferromagnetic k equals to gamma point. And basically, there is a non-abelian bosonization formula for the spin operators that is natural to write down in terms of the field theory. So this field theory is written in terms of currents that are called left and right Wess-Zumino currents. And sigma is a Pauli matrix, and then we have the SU2 field G that is this kind of SU2 matrix that we are left with a low energy when we gap out our Hubbard chain. And so, but the main result of this field theory, the main prediction, if you want, the main result is this equation below. That is the behavior of the spin-spin correlation function at large distances, so at low energy, in this that are coming out naturally from the field theory. And as you can see, this is given by two contributions. There is a uniform part that does not oscillate in space, and there is an alternating part. This is what we are used to, right? So this is an Eisenberg antiferromagnet. So it's, as I was telling you at the beginning of the talk, that this can be also obtained from Bethe ansatz. We have an alternating part, but also we have a uniform part. And this comes naturally from this field theory approach applied to the Eisenberg model, right? So
Alberto, can I ask a question? What are not in the oscillation part then?
R naught is it's a parameter.
Okay.
It's just a parameter, right? It's just a parameter, right? That is kind of convenient to write down as logarithm of square root of the logarithm of R divided R naught, right? If you want, it's just a constant that comes naturally when you solve the field theory of this of the model, right? The field theory Lagrangian that was this part of the Lagrangian. Of course, you neglect the part that is gapped out, right? Because you are interested only in the low energy in the low energy part, right? So yeah, that's the main point, right? So the main point is out of all this discussion of the field theory, the main result is that you can write your spin operator, and A is the lattice constant. So if you want, there is a passage between the continuum and the lattice, right? And this is the formula from the continuum you go to the lattice, right? Or vice versa, if you want. And yeah, this is very important because now we want to perturb, because now we have K and gamma again. So until now, I just talked to you about the SU2 symmetry point that is hidden, that appears when K is equal to gamma, but now we want to put perturbation around it, right? And when we do this and we try to, and we express these spin operators in terms of the field theory, using this formula that I'll show you in the previous slide. Here, yeah, I'm saying something that I'm going to introduce later. I'm sorry, but yeah, these operators, they should kind of respect the symmetries of the model in some form, and I'm going to be trying to that are discrete. They are not, you know, our model to start from is not SU2 invariant, of course, because there are many. There is the Kitaev, there is the gamma, and of course there is no SU2 symmetry. I'm going to show you later that the symmetry group of the model is isomorphic to the full octahedral group, including inversions. And but the main point, without going into details, is that when you express this perturbation in terms of this Wess-Zumino current, only SU2 terms are possible in the sense that they respect the symmetries of the model, right? And so this tells us that this SU2 symmetry that was just present at this hidden point K equals to gamma should be extended in a finite neighborhood, in a finite region, right, around the K equals to gamma point, right? This is the main message. And so now I'm going to go into a little bit more details. So what Ian and Wang have proposed is the generalized bosonization formula to go from the lattice to the continuum, or vice versa, if you want. But now there are complications, of course, right? There appear coefficients D and C that have to do with the fact that the symmetry group of the model is discrete and not continuous, right? And associated with the fact that K and gamma are different, if you want. And but at the end of the day, the main prediction that Ian and Wang brought to me was this new formula that should be valid for K different than gamma, if you want, not too far. The original assumption was that K and gamma should be different from each other, but not too much. But this is the new formula, right? That we need to verify numerically to see if these field theory predictions are verified, right? So again, this parenthesis n means that there is a periodicity of 3 sides, as I was telling you in this model from the start, right? So from in this rotated frame, right? And so that's what I did, right, with using the MRG calculations. And so first of all, the first thing that I verified is that the spin-spin correlations go like 1 over R and are staggered. So this is an antiferromagnet in this, again, rotated frame. And here, this plus lines, straight lines with fits just means that we have a log-log scale. And so that just means that the correlations go like 1 over R with so the exponent should be -1. And here I'm showing what happens for K equals to gamma. So that is our beloved SU2 hidden symmetric point. And 1.15 times pi is K different than gamma. So this is a kind of numerical demonstration that things are working, right? The field theory predictions are very precise. But for now, I'm assuming that this square root of logarithm was not present. So I was assuming that this was not there. But then it's also useful to verify that this square root of the logarithm corrections, the so-called logarithmic correction to the 1 over R, the power law behavior, are also present in this model. And I must say on the side that on a lattice, we did this on a lattice with periodic boundary condition. That was very hard, using a lot of states. And of course, the distance, the notion of distance on a periodic chain becomes a chord function, sine of pi over L. So when you do these fits, you should be kind of a little bit more careful. And so we went ahead to verify the logarithmic correction, as I was telling you a second ago. And this was done in a kind of indirect way by extracting the stagger part of the correlation, multiplied by R if you want, and squaring the result. So if you do this operation, assuming that this relation holds, you want to extract the log R behavior from here, right? So what you do is multiply by R and try to kill the -1 over R, right? And when you kill the -1 over R, you automatically kill also the uniform part, right? So this is, I hope is clear. And again, we find a very good behavior for K equals to gamma and K different from gamma, right? And so, and we did the same for the uniform part. So there are tricks that are now almost running out of time that you can do to extract to verify that this correlation function has also a 1 over R square behavior over here. In the uniform part, and that's what we verified here. Again, it looks like a decrease with the slope -1, but we just took the uniform part of the correlation function multiplied by R to extract again a 1 over R behavior. The last thing that we did, that was the most complicated one, is to to extract these two coefficients here because of symmetries, and I don't have time to talk about much about symmetries. These coefficients here, they are not all independent. That would be kind of a nightmare. But there are only two that are different from each other, right? And we extracted them by looking at the asymptotic behavior of the correlation function and verifying that all the prediction from these formulas were verified, right? So this is a very technical slide. If you have question about it, please go ahead. But I would like to proceed and go into the other phases of the phase diagram. Just to give you an idea of the work, the other work we have done. And so, yeah, and this is was another result that we verified that C1 and these parameters are really 1 if you are at the exact antiferromagnetic point, and they deviate from 1, But the main result here is that the region of validity of this field theory prediction verified numerically extends a lot away from the antiferromagnetic hidden SU2 point. And that was the main result of the paper. But there is a caveat in all this. So until now, as I told you, I worked in this 6 sublattice rotated frame. But when you look at the results in the physical frame, if you want in the physical system, you need to also always transform back the correlation function that they look antiferromagnetic. In the rotated frame, they look like ferromagnetic, like a non-collinear, very complicated one, very complicated pattern in the original frame, right? So that's something always to talk about, to think about, sorry. Yeah, so going back to the phase diagram, this is kind of exhaust this pink region of the phase diagram that we verified to be kind of hold for an extended region, not just around the antiferromagnetic point, but all the way to the minus, almost touching the ferromagnetic Kitaev point to this phi c, to the first order phase transition point. But let me discuss for the last few minutes of my talk the order phases that are also interested. And here in this plot that I'm showing here, I'm showing the ground state degeneracy that I was able to compute using exact generalization for a small system, looking at this across this region here from phi equals to 0 up to 0.4, right? And what you can see here is that the degeneracy jumps abruptly as a first order phase transition from basically non-degenerate ground state that is typically of conformal field theory or low energy field theory fixed point. That is also conformal, that it was something that is standard, but I didn't mention yet before. And so the degenerate jumps to a number that is very high, to 6. And so here in this plot, there are these names, OH down to D4. So, and also from this plot, it looks like the degeneracy jumps also to 4. And we know that the Kitaev region of the phase diagram, and that's also something that I verify numerically, the degeneracy of the ground state is exponentially large, so it doesn't fit, of course, in this plot because it grows with system size, and I was not able to extract the degeneracy of the Kitaev of this region from the numerics using a small system. But let me discuss these two order phases that I call OH down to D4 and OH down to D3. What are those phases, right? That's the last thing I want to address. And actually here, I give you a more kind of a detailed view of the phase diagram with the particular phi prime and phi 2 prime values at which angles this kind of transition happen. And very quickly, so this is what is this OH down to D4 phase. So let me go back to, I'm showing you now what are the symmetries of this model on the lattice. Again, we are in the 6 sublattice rotative frame, so we have several symmetries, but one was good enough to show that doing the group theory analysis, that the symmetry group of the model is isomorphic to the full octahedral group, right? That has dimension 48. So it is basically, from a geometric point of view, it's equivalent to the symmetry group of a cube, right? I'm not going to go through all this symmetry operation that translate to that when you combine them together, they act like the group definition of the group definition of the octahedral group. And so let me go back to this order phase. This is not what you expect from a classical spin point of view. So if you solve the model classically with classical spins, you don't observe this symmetric breaking pattern from this OH, from the full octahedral symmetry of the problem down to a subgroup of reduced symmetry, that is this D4, right? So this D4 is the dihedral group, but is geometrically equivalent to the group of the symmetry group of the square that has 8 elements. So basically, this degeneracy 6, what we found out is that it comes from the fact that the unbroken symmetry group has dimension 8, and since the symmetry group of the model has dimension 48, when we divide 48 by 8, we get 6, and that's the 6 degenerate states that we found in the numerics, right? And here I'm showing you the spin orientation of these 6 degenerate ground states. You can geometrically think about them in the sense that basically the spin of the unit cell of this 3-site unit cell is pointing basically in the one of the 6 faces of the cube. Basically, that's what we want to think about this in this term, right? They have a very kind of simple. Again, it's not the direction of a single spin, but imagine to combine 3 spins together in the unit cell in a smeared, if you want, big spin, so-called, and take the center of mass of the orientation of these 3 spins. The 6 possible states that we are talking about here have spins in the sense of the unit cell orienting in the 6 possible faces. Pointing towards the center of the 6 possible faces of the cube. And that's the meaning of this symmetry breaking OH down to D4 order phase, right? Again, this is all in the rotated frame, so we should take this with always a grain of salt, in the sense that we should always rotate back to the original frame of reference of the original Hamiltonian. And that's what I did here. Here it's what I was trying to explain. So in average, in the unit cell, the spins are pointing towards the center of the faces, the 6 faces of the cube. And this is the speed pattern that you should observe. The speed pattern in the rotated frame, if you want, is purely ferromagnetic. But then if you rotate it back in the one of these states, one of the 6 states, and take the speed pattern and you rotate it back to the original frame, you get something that is very kind of distorted and acquires also a periodicity 6 because of the 6 sublattice rotation, unitary transformation, right? And finally, so we also discussed that we also verified, we did some other checks that this is really the case, that this is a 6-fold degenerate ground state. I'm not going to talk about that because I don't have time, because I think I'm 2 minutes left. Is that correct, Chrisia? Or I'm already...
Yes, we have to, we have 2 minutes because we were delayed in the beginning.
Okay, perfect. So I have 2 minutes. So because we have 2 minutes, we also checked the emerging correlation. I'm not going to have time to discuss the OH down to the 3 phase. That is the phase that it's realized classically. If you think about the spin in classical terms, and you you solve the model classically, you minimize the free energy of a classical Hamiltonian, you get a different pattern, not the OH down to D4, but you get the OH down to D3. And I verified that this is the case. This time, the degeneracy is not 4, as I was finding with the exact generalization here, but the degeneracy of the ground state should be 8. And we verified that by looking at long range, the correlation, some specific correlation function that are respecting the symmetry of certain symmetries. And we verified that they show a long range order at long distances, right? So the pattern here as the degeneracy 8. So if you want, as you approach the Kitaev point, the antiferromagnetic Kitaev point, the degeneracy of the ground state is going in step of 6, 8, infinity, if you want. And yeah, so the final thing in the very last minute is the we worked out the full phase diagram, including the Eisenberg J. Of course, I don't have time to go into these phases unless you are interested. But the final thing I wanted to tell is that many theoretical works are coming out about these one-dimensional Kitaev magnets, and this is probably a partial list, and I apologize if someone is not included. And also, very last thing, tuning the dimensionality of this Kitaev, of the 2D Kitaev materials are shown to be possible in this beautiful paper, actually of 4 years ago, where they were able to construct chains, not of the Kitaev materials, but they were thinking about here of strontium iridate 04, that is the standard spin-orbit Monte insulator, by a smart way of growing the transitional metal oxide on top of the substrate, and in a direction perpendicular to the plane, if you want, to the several planes that are on top of each other. So you should see this picture to rotate it by 90 degrees, this picture over here. And also the dimensionality has been shown to be also possible by in this recent paper on lithium rhodate oxide, where basically, while in the usual Kitaev materials, by applying high pressure, you would typically dimerize them. For this particular new class of this particular material with as rhodium, here it has been shown that the distance along the z direction on the black curve here, the distance rhodium, that is the z interaction that we neglected in this paper, in this talk that I neglected, the distance grows as a function of pressure, but it decreases along the x and y direction. That is basically you form zigzag chains weakly coupled together by applying pressure on this material. And here is a list of things I'm working on right now, and which means characterizing better the Kitaev phases and applying magnetic field. There is also interest in higher spin S Kitaev material, and we have done some work on that as well in the chain case. And also current work is the excitation spectrum of in relevant phases, of course, for this model that we treated, that should be relevant for neutron scattering, resonant inelastic X-ray scattering experiment. And with this, I apologize for the delay, and I thank you for attention.
Beautiful talk, Alberto. Thank you very much. We have few time for questions. Noah Bradley has a question. Try to unmute yourself. Can you
hear me now? Hey, Christian. Alberto, this is Noah Bradley. So the question, you have all these open questions, and I got to put a list on number 4 on this one. Okay, so maybe It's not an open question, it's a closed question. You already have the answer, I'm hoping. So the honeycomb, okay. The honeycomb parent Hamiltonian, whose ground state has entanglement spectrum described by the same WZW fixed point that describes the gamma equals k Kitaev model in 1D. That's the question. What's the parent Hamiltonian? What's the parent Hamiltonian who's in the honeycomb, or say maybe it could be a square lattice or something, that has entanglement spectrum for the ground state, take the ground state wave function on a torus or something, and do some cuts and look for the entanglement spectrum a la Haldane Lee. And for the honeycomb Kitaev model with the magnetic field, the fancy one, the entanglement spectrum is described by single free Majorana fermion, chiral Majorana fermion. This C equals a half, the quantum Ising fixed point. And so the kind of coset construction, is well, anyway, in field theory language, there's some words for it. And we wonder what the parent Hamiltonian might be on a two-dimensional lattice, whose entanglement spectrum gives us the fixed point that controls the 1D gamma equals Kitaev model.
Yes. So the question is, the answer, the straight answer is that I don't know. The question should probably address more to Wang and Ian, that I worked more than me on the field theory part. So that's a straight answer.
I guess it's a lattice level question. I mean, I guess that a field theory wouldn't help.
The lattice level, yeah. So
so what do I got to do on the honeycomb so that I get a entanglement spectrum that looks
2D,
like?
I don't know. On 2D, I don't know. So what?
No, but I think you may be the one to ask, because you did it as 1D, right? And so you get an energy spectrum, let's say. I mean, you get a lot of stuff, but let's imagine we get the one that you showed in the beginning with the spin-ons, right? So you have some spin-ons, right? And now we're going to look for those spin-ons in the entanglement spectrum of the ground state wave function of some honeycomb model. And I guess you'll be the one to ask, because you're working with lattice models. So we're looking for some lattice model that tunes away from the boring Majorana fermion that the honeycomb Kitaev model gives us, that we know and love, but it's it's boring. Now we want a Luttinger liquid with C equals 1, described by this fancy field theory stuff, right? The one that you get for the gamma equals K.
Yeah, but
so what do we got?
Model in 2D, right? You don't want to model.
Yeah, what do I got to do in 2D so that when I cut it, I get the SVD spectrum looking like the energy spectrum that you find in 1D?
Yeah,
that's the question.
Yeah, that's a very good question.
May have a simple solution, right? Something like we tweak this parameter, tweak that parameter, but maybe not. Maybe we got to think about symmetries.
Yeah, so I know that there is a paper out there already where has treated the coupling between the chains, right? To turn on the coupling between the chains, and with Monte Carlo, using Monte Carlo, but you quickly
have
gap,
issues.
You quickly gap this this CFT, this couplers. You gapped it, right? And also there is another work that is numerical that I hadn't time to talk about by a young Eric Sorensen and collaborators, where they couple two chains together on the vertical, two chains together as a honeycomb strip, like two-leg ladder. And they show here in the region where everyone is interested in that you gap the spin liquid, right? So in 1D, you have this the CFT with C equals to 1 that I talked about today, and into the leg ladder, you have the already gapped spin liquid phases. Right?
So that's what we have in mind, is we want a gapped spin liquid in 2D, right? So then when we do the entanglement spectrum, we get there's a famous entanglement gap. Like think about like a quantum Hall liquid, right? We want a gapped incompressible fluid that has this C equals 1 on the edge, right? And so that's a perfect direction, right? We've coupled two kind of chains that we understand, but now how do we make it? Do we just keep going? So to take this model and just keep adding ladders, and you think, if it's 4-leg.
Weakly coupled ladders would be a kind of a good direction, I think. So in the sense that you want to preserve the gapped So this works like, at least in this region of the phase diagram, we can easily understand it works like an Eisenberg model that is capless in 1D, and then we couple two chains is capped, right? And then even and odd, right? We have this even and odd effect where for even number of chains is capped and odd number of chains is capless. So it would be nice to go verifying towards that direction that it stays like.
But that's okay. But that's too simple, right? Because that's like what they call like a columnar dimer or something or other. It's an ordered phase, and it's not the long range entangled, you know. Because if you cut it just right, you don't get any entanglement, right? We need something more.
I see.
Something more like AKLT, but in 2D, you know. So like in 2D, right? So we want a dangling spin 1/2 on the edge, and then what are they going to do? They got to quench their spin entropy. They're going to do a C = 1 CFT, something like this, right?
I see. There was another work recently by He Yang about dimerizing the Kitaev gamma chain. So like
gapping it out, yeah.
So you gap it out, right? So because you think that 1D system in reality, you always have a spontaneous, like you have pairs dimerization possibility, right? That is probably very, very realistic to think about. So they have studied the bond alternating, right? So by just dimerizing the strength of the Kitaev gamma. And they've worked out the phase diagram again also there, right? So the field is kind of exploding. This is the paper I'm talking about.
So so you imagine you have one. Yeah. So you imagine you have a torus, right? In 2 dimensions, honeycomb. You wrap it on a torus, and then we make 2 cuts. Boom, boom, right? And it turns it into cylinders. Now we kiss those cylinders together, and the C = 1, you know, fixed point that you've been studying, it has to gap out when it touches the other. And so we're thinking about, in this language, what we're thinking about is, what are the natural ways to gap out a C = 1 guy by kissing him to another? Dimerizing is an obvious solution. But I guess the question is something like, when we bring the JL and JR together, right? They get the square root of log correction, right? From the coupling between the chiral sectors, right? So it's something like, we want to kind of do like an RG where we, you know, like in the original Wilson RG, he was thinking of 3D for the Kondo problem. He's thinking about a critical fluid, Fermi gas, right? And looking for a change in the boundary condition that comes from the formation of the bound state. And that crossover tells you the Kondo temperature and all the rest, right? So similarly here, we have this gapless mode on one edge of the cylinder, you know, when we do the entanglement cut in 2D, and we're kissing it together with the other, with the right mover, and we want them to kind of gap out.
I see.
But what we're looking for is, as we change the interaction, so say in the Kondo case, change the band structure, change the coupling between the spin and the fermions, the s electrons, we want to see how that crossover scales, and in this way numerically solve the thing.
I see.
So it sounds like we have a lot of ideas for how to make a gap. We can do dimers, we can do 2-leg ladder.
Yes.
But the issue then is how to kind of convert this a la Wilson into a parent Hamiltonian in 2D.
Yeah, that's I don't have a straight answer to that at the moment, but yeah, something that I will think about. Need to think about. Yeah, I have only the simple answer at the moment. Yeah.
All right. Well, thank you very much, Noah, for your questions. And thank you again, Alberto, for this nice seminar. And hope to see you soon with a lot of fun with this project. I'm very curious to know about the rigs and the INS.
Yes. Thanks again, everyone, for having me. Thanks.
Bye. See you.